Okay, today's lesson is about Euler paths and circuits. And let's see. Lesson objective. I can use graphs and the definitions of circuits and paths to study a situation like the Koningsberg Bridge Problem to determine if certain conditions can be satisfied. The Koningsberg Bridge Problem. Following figure shows the rivers and bridges of Konigsberg. Residents of the city occupied themselves by trying to find a walking path through the city that began and ended at the same place and crossed every bridge exactly once. So let's see if that's possible. Say we're the mayor of Konigsberg, and he's going to start right here on the north bank of the river. He'll cross the bridge to the first island, and then he'll cross this bridge over to the south bank of the river, over to this bridge from the south bank over to that island again. He's going to cross this bridge to the north bank of the island north bank of the river from the island, and he'll go back down the bridge to this other island, and then down this bridge to the south side bank. And there's no more bridges he can get on because he's crossed all the bridges from the point where he's at. He can't get on this bridge. He's already been on it. Can't get on this bridge. He's already been on it. So he's crossed 6 of 7 bridges, and he hasn't crossed this bridge. So let's see why that's happening. All right. The bridge problem is a graph. Leonid Euler, who was a famous mathematician, turned his attention to the bridge problem. His first step was to model the bridges of Konigsberg with a simple graph. The points, or vertices, these big, bold dots, represent the land, and the edges, which connect between the 2 or more vertices, represented the bridges. Now, Euler's map of Konigsberg, while much simpler, conveyed all the necessary information about which parts of the land were connected by which bridges. And it looked like this particular graph. All right, now let's state this bridge problem a different way. Given a graph, find a path through the vertices or points that uses every edge exactly once. Such a path is called an Euler path. If an Euler path begins and ends at the same vertex, it is called an Euler circuit. Okay, basic concepts of graph theory. A graph consists of vertices and edges, and we'll define what those are here in a minute. And the singular for vertices is vertex. We know that word from when we were talking about parabolas in algebra. And I think vertices exist in ellipses too. So anyway, a vertex is a thickened point or node. And I just said we would define that. So those big points, those are vertices or a vertex in singular. An edge connects or bridges between 2 vertices. It could connect a vertex to itself. And we'll look at an example of that here in a second. Edges are drawn as line segments, arcs, etc. Multiple edges between the same 2 vertices is sometimes allowed. If you look back here, there are multiple edges between these 2 vertices. Same here, multiple edges between these 2 vertices. If you want to look back even further, this would be a vertex, this particular side of the river. The island here would be a vertex. This side of the river would be a vertex, and this island would also be a vertex. And all these bridges would go to that one vertex, the south side of the island. And it looks like this as a graph, okay? Those are the definitions, and let's look at some examples. All right. This first one, let's see, is a path or a circuit possible? Not sure. Without a plug and chug method where we just go ahead and just try and use trial and error, there's no other way to know because we don't know enough about graph theory to actually use what we can learn to the best of our ability. So let's keep moving on. How many vertices does this have? A, B, C, D. There's 5 vertices. How many edges does it have? 1, 2, 3, 4, 5, 6, 7. Okay? All right. Graph examples. Here's the second example. How many edges or how many vertices? There's 7. And how many edges? 4 and 5. There's 9. Okay? And let's move on. Euler's contribution. Now, Leonid Euler paved the way in solving many computer science problems of today by creating a new mathematical discipline called graph theory centuries before the first computer was created. Now, we can speculate as to how that helped us now, but unless you go into the computer science discipline, it really isn't really important to know how it helps them unless you're actually going to need the help he contributed. All right, so let's move on. Definitions here. It's very important. This is vocabulary you need to remember. It's going to be helpful and useful for you to learn what you need to learn for this particular lesson. A graph in which every edge is crossed only once, which starts and ends at the same vertex, is called an Euler circuit. So we know what the word circuit means. It means something that goes around to itself, right? We take a bus circuit. If you stay on the bus long enough, you'll end up at the same spot, right? So an Euler circuit simply means you're going to touch every edge on that particular graph exactly once and start and end at the same spot. A graph in which every edge is crossed only once but starts and ends at different vertices is called an Euler path. That's like a map where we cross every edge in the city, but we end up at a different spot where we started. Okay, so let's move on. Let's determine if the following graphs are either Euler circuits or Euler paths or neither. So let's start at A, and let's see if there's a pathway between all of the edges and touching, starting and stopping at the same vertex or starting and stopping at different ones. So let's go A to C, C to D, D to A to B, B to D, D to E, and then E to B. So I touched every edge exactly once, but I didn't start and stop at the same vertex. So what's that called? A graph in which every edge is crossed only once, but starts and ends at different vertices is called an Euler path. So this first graph is an Euler path. All right, this next one, A, C, F, D, A, B, E, G, F. Well, we almost touched every edge. We left this DE edge out. So we're not going to explore that further. Let's just say, for all intents and purposes this time, it is impossible. How about this one? 1, 2, 3, 4, 5. Well, I can't get back to 6. I could go to 2, but I'm still missing this edge and this edge. How about if I start at 6? Around to 6, 4, 3, 2, 5, 1, 2. I've touched every edge except this 5, 4. So not sure if that can actually be a path, and I'm pretty sure it can't be a circuit. So let's look at some things. All right, the degree of a vertex. The degree of a vertex is the number of edges that connect to a vertex. Now this can be confusing, but it is easy to determine. If an edge loops back into the same vertex, it counts as 2 edges for that vertex. Now if an edge connects 2 vertices to each other, it counts as 1 for each vertex. All right, let's look at the degree of the vertex in the first graph, this top one. How many edges connect to A? There's one from C to A, from D to A, and from B to A. So there's 3. A has a degree of 3. How about C? There's one from A to C and D to C only. So that is a degree of 2. How about D? C to D, A to D, and B to D, it's a degree of 3. Okay? Oh, wait. There's an E to D. It's actually a degree of 4. B, A to B, D to B, E to B, degree of 3. And E has D to E, and B to E, it's degree of 2. And you guys can do the others to find out what it is, the number of degree of vertices in the middle and the degree of vertices in the bottom, what they are. Now, this bottom one, remember, this loop right here means that 6 has 1, 2, 3 edges, okay? So it is a degree of 3. All right, let's move on. Now, what makes a graph an Euler path? And then what makes a graph an Euler circuit? And how do you determine that neither an Euler path nor an Euler circuit actually exists? So let's start at the top. An Euler circuit exists in a graph when all the vertices are of an even degree. So that means all the nodes or the vertices are divisible by 2, or have a degree that is divisible by 2. And an Euler path exists in a graph when 2 vertices are of an odd degree and the remainder of the nodes have an even degree. And then neither an Euler path nor an Euler circuit exists in a graph when there are two or more vertices with an odd degree. Now, I can explain this easily. Think about it this way. If you leave your house and you come back to your house, you have to go through a door and you have to come back in a door, right? So let's say the door is the edge between the outside and the inside. So in order to touch that node, your house, starting in at the same point, you have to have an edge that goes out of the house and into the house. Notice that there's two, out and in. So if you wanted to go out and in a million times, there's always an entry or an exit and an entry. So there's always two. So divisible by 2 means and makes a lot of sense. Okay, so let me launch you with this. Leonid Euler introduced much of the mathematical notation that we use today, such as the notation f of x, or the function of x, that describes a function of the modern notation for any trigonometric functions. Anything. Function of x, whether it be quadratic or sinusoidal, it doesn't matter. That function of x, he created it. He also was the first to use the letter e for the base of the natural logarithm. That was named after him and is now known as the Euler's number. You've used that before. So anyway, go back through this and watch it as many times you need to. That's the best part about videos when it comes to lectures. So if you have any questions, please just go back and look at the video again. Have a great day.